Well, here we've got a problem with galvanic or cells, named after Luigi Galvani. And there are a bunch of chemicals that you can mix together, and you're going to try and get them to run an electric current through a wire. So let's look at the chemicals we've got. We've got some chromium. You're used to chromium. That's a metal that you'll find that they used. And very often they'll have it alloyed with iron. And then, of course, aluminum. You've seen aluminum around. I'm pretty sure, if you looked around, you'd find some chrome-plated steel somewhere. And I'm sure some aluminum is within reach of you right now. So those two you know about, nice shiny metals. Remember, metals have got their electrons, their sea of electrons. They're conductive of electricity. The two solutions that we've taken an ionic compound. Now, you see here aluminum chloride, and your knowledge of charges by now, knowing that aluminum has a +3 and chlorine has a -1, should allow you to understand this formula. Aluminum chloride is pretty common. It's used in antiperspirants. It absorbs water very, very nicely, and then it produces sort of a thick gel that clogs pores to prevent sweating. So you'll find it almost in most antiperspirants. There are some that don't have aluminum, but the effective ones generally do. In a solution, this is soluble in water. Most chlorides are soluble, except for silver or lead. But this will dissolve very, very well in water. In fact, if you have pure aluminum chloride and you open up the bottle, you'll see some fumes as it tries to suck humidity out of the air. It's like super, super absorbent, hygroscopic actually. So this is going to be a clear solution. I've got a light gray. Chromium, a transition metal, is pretty notorious for having all sorts of brilliant colors. Here's a example of chromium 3. They use the 3 to warn you that it has a +3 charge. There's a chromium with a +2 also. And when it's pure, it's purple. Chromium is very unusual in its d orbitals. You would expect, with what you know about d orbitals, for it to be a 4s2 and a 3d4, but actually it takes an electron from the 4s and has an unusual structure, a 4s1 and a d5. It steals things, and with that weird structure, you end up having these colors. As soon as you get some water around it, it turns green. So chromium is a lot of fun to work with, but you've got to be careful. It's a hazardous material when it's ionic, and you can't dump it into water and so forth. You've got to be trained to work with it and dispose of it. And here we have some solutions. Here's the very light ones, and notice as the solutions get darker and darker, they're more concentrated. And a 1 molar solution you wouldn't be able to look through it very well. These probably are maybe like 2/10 molar over here in a test tube. And you know that we can tell concentrations by how much light goes through a solution. So here I've got the solution tinted slightly green, so you could differentiate it from the aluminum. Don't have to worry about the chlorides. They're pretty much spectator ions. And you can see from this reduction chart the importance of things. Notice what's given here is we've got chromiums, and they grab electrons. These ions, will pick 3 electrons up. They become this beautiful, shiny, metallic chromium. So these chromium ions are going to attract electrons. This is a reduction chart that tells you these materials on the left are going to, this should be almost, attract instead of plus, attract electrons to become their metals. And this is pretty typical for cations of metals, that they'll attract electrons to various degrees. And the degree of that attraction is listed by their voltages. Now, here you can see a -0.74. Now, that doesn't mean that chromium ions don't attract electrons. No, it just means that they don't attract electrons as well as hydrogen ions do. Hydrogen ions are pretty good at attracting electrons to become hydrogen gas. And chromium ions aren't nearly as good, so that's why they have a negative. So this is a relative attraction. Doesn't mean that it repels them, no. It just says we're not quite as good as hydrogen ions. And you can see aluminum is not nearly as good as chromium. It's got a negative 1.66. So here's our scale, our reduction. These are listed as volts. The volt involves coulombs and joules of attraction. Joules of attract these things. So what's better at reducing? Now, don't worry about the metals here because they're here on this side. If you're looking for things for reducing, you look on the left and you can see the chromium is better at grabbing electrons. Now let me quickly go to this image. Remember, electrochemical cells are an arrangement where you've got two substances trying to pull in on electrons to reduce, to gain that negative charge. And the one that wins is going to get the electrons. It's going to get electrons. Now, the battle is going to be between the metal that has the electrons. This is what's going to lose the electrons. So it's a battle between chromium trying to grab electrons from aluminum and aluminum trying to grab electrons from chromium, and chromium is the winner. The chromium bar here is not going to do anything. The chromium ions here are going to tug on the electrons of the aluminum and take them away. And the aluminum will change into aluminum plus 3. So the aluminum plus 3 isn't going to be involved in this reaction. It's the aluminum metal that is going to lose the electrons. So we've got the idea here. We'll talk about salt bridges in another video. So let me go back to my problem and see if I can get the right video here. I've got the right one going now. So the substance here that's better at reducing will reduce. The chromium. It will grab electrons, and it can grab them. These chromium ions here, this green stuff, will use this conductive wire and take electrons from the aluminum. The aluminum, the lower substance, will go backwards. Remember, when you have a reduction chart in order, the top substance will go forward and the bottom will go backwards, will oxidize. So what's going to oxidize, what's going to lose the electrons, loss of electrons is oxidation, is the aluminum. So here's our reaction. Aluminum giving its electrons, not giving, it's going to have its electrons ripped off by the chromium. The chromium is very good at pulling electrons, and the aluminum is going to end up losing them. By the way, hydrogen would do the same thing. Hydrogen would take electrons from the aluminum and also take them from chromium, but chromium has an oxide layer, so that's why it doesn't happen all that often. So as a reaction, we have the chromium ions turning into metallic chromium. You'll see little crystals of chromium growing on here, metal crystals. At first they look sort of black because very, very small particles of metals are black, but as they grow bigger, they'll turn into beautiful metallic, pure, extremely pure chromium. In fact, that's one way you can purify metals is through this type of a reaction. In fact, your copper that you have in wires has been made that way. And somebody's going to lose the electrons, and this aluminum bar does. And the aluminum bar, of course, is going to wear away. It's going to look like it disappears, but it's going to turn into this aluminum plus 3 into solution. So this aluminum ion, these aluminum ions will increase in concentration because we're losing the aluminum bar, and the chromium ions will decrease in concentration because they're turning into chromium metal, and the electrons will be coming in this direction. Okay, so oxidation, loss of electrons, aluminum turning into aluminum plus 3. Reduction, chromium ions turning into chromium here. This chromium metal is really unnecessary. You could have a graphite bar or anything that conducts electricity, and you'll see the crystals growing on it. Now, what's the voltage? Okay, now, I hope you remember we have an equation. for the voltage. If you want to find out what the voltage will be, what the net pull on these electrons is, it's electromotive potential is what they call it. You take whatever reduction potential you have at the cathode. Oh, you know, cats reduce. I'm not going to go too far on that. The cathode's always where we have reduction, period. Cats reduce. So top substance is going to be our cathode, and its standard. Notice we have a 0 here. And I'll explain that 0 in a second. Minus the reduction potential here. Remember, it's a tug of war, and basically the chromium ions are going to win. These guys are going to resist, and that's where we have this negative here. So we would then take this and say, what's my voltage? Our cathode, negative 0.74 minus our negative 1.66 volts. Be very, very careful when you do this on your calculator. It's really easy to mess up on these negatives. Spend a few extra minutes checking to make sure you've got your signs right. Common error in these problems is to forget a negative. So it's cathode minus anode, and we use these reduction potentials. Some people say, well, always change the sign of the oxidized material and add them. I find I get the most success with this. Okay, so how do we get the voltage? Find the top, subtract the second. We know the top will go forward and the bottom will go reverse. Now, what's this Q thing? That's our equilibrium. Well, we've got a reaction here, and here's our products, and here are our reactants. Now, remember, when we were dealing with equilibrium constants, that we would take the products over the reactants, and any coefficients would become superscripts. And that's what we get for our Q. And we only use, in this case, we're dealing with concentrations, not pressures, the concentrations of the stuff in solution. Well, that's the concentration of the aluminum over the concentration of the reactant chromium. We ignore the solids. So the Q is pretty simple on a lot of these electrochemical cells. Sometimes you'll have exponents if you've got coefficients in your balanced reaction. So that's it. So what's the answer for Q? Well, this is where we get back to our E. If you're looking at a tug of war, which we have here, to be fair, you have to make sure everybody is on equal standing. You have to make sure that everybody has the same concentration of ions. If we're talking about chromium ions pulling on electrons and aluminum ions pulling on electrons, we have to make sure their concentrations are the same if we want to compare them. It'd be unfair to have different concentrations. That's the Nernst equation. So the standard arrangement is that, whoops, let me get back to here. The standard arrangement, when we have this E0, the standard arrangement is for our solutions to be 1 molar. And if we're dealing with gases, that's 1 atmospheric pressure. Now, given here, the galvanic cell setup has 1 molar solutions. So 1 molar of this clear antiperspirant solution and 1 molar of this chromium green that's used very often to chrome plate things. So Q is 1 for any standard cell. Whenever we're dealing with E0, everybody's starting off at 1 molar. Now, what's the actual K that a reaction will move towards? Well, if you have a voltage that's at all positive, if it's even like 1/10 voltage, you get a huge KEQ. I calculated this. The calculation for this is a bit involved. You've got to use delta G, and then there's another delta G, and I set things up, and I solved for the volt or for the K on this, and you get 10 to the 15. And as I say, generally you should know that if the voltage is positive, you have a huge K. In this case, 10 to the 15. So this K means that if you're starting off at 1 molar, this reaction is going to go forward. This cell is going to keep on going as long as we can get over the activation energy until this all of the chromium ions are gone, changed into the positive chromium. This is typical for a cell. The reduced substance, if you got a positive voltage, is going to, those ions are going to be completely depleted, and this is going to change into as concentrated as you possibly can get. Imagine the concentration to get 10 to the 15. This chromium is going to have to be very, very small and divided into the aluminum. So I hope that helps you a little bit. Important things to remember: this reduction chart. The stuff on top reduces, the stuff on the bottom oxidizes. The voltage is the top minus the bottom. Under standard conditions, Q is 1. And it's going to be shooting towards a huge KEQ if you have any type of a positive voltage. Okay, hope that answers your questions.